Okay everyone, my name is Zheng, metric number 271781. And my partner Cheeh Hui Min 271917. I would like to present the application of calculus in banking. So first of all, introduction. In this section, we will discuss what is calculus, what is calculus rule, what is banking, relationship between banking and calculus, and the importance of banking to our work. So what is calculus? Calculus is a branch of mathematics that involves the study of rate of change. And calculus was invented by Isaac Newton and Gottfried Leibniz. Okay, next one, what is Laplace rule? Laplace rule is a theorem in calculus, and it is named after a French nobleman called Guillaume Ponce Andre Marquis du Lotto. This will be further discussed in the method section. Okay, next. What is banking? Banking is defined as a business activity of accepting and safeguarding money owned by other individuals and businesses, and then lend it out to execute economic activities such as create profit or cover operational costs. The history of banking came when empires needed a way to pay for foreign goods or services. Okay. So what's the relationship between banking and calculus? Actually, everything related to banking can be calculated by using calculus such as interest, currencies, savings, and many more. Besides, calculus also helps people to manage their bank accounts easily, like income and expenses, because people who learn calculus will be more sensitive and alert to the numbers. Okay, so what's the importance of banking to our world? One of the importance is the banking system can collect the savings from people, then lend them to businesses and manufacturers. In developing countries, I measure the banking system is very important as it is a major source of fund. Furthermore, the banking system also helps in both domestic and international trade. This is very important as in international trade, since the partners are often strangers who live in separate countries. Okay, the next section is key concepts. There are various types of key concepts that are related to banking. However, the concept that we would like to discuss here is the continuous compound interest. Continuous compound interest is the interest calculated on both in the initial principal and all subsequent interest. The concept in that the principal will be paid interest on a continuous basis rather than in discrete amounts at specific times. So the functions of key concept is A equal to PE or RT. A stands for amount, P stands for principal, R stands for interest, and time stands for time. Finally, the method we have chosen to tackle the key concept mentioned before is Laplace rule. Laplace rule says that the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. In other words, Laplace rule is suitable in calculating continuous compound interest. Below is the basic function for Laplace rule. That's all for me. The rest of the part will be presented by my partner, Cheeh Hui Min. Thank you.
My name is Cheeh Hui Min. Metric number is 271917. Today I will explain examples and analysis. Example 1. The formula for the amount of A in a savings account compounded n times per year for t years at an interest rate R and an initial deposit of P is given by the formula, which is A equal to P bracket 1 plus R per n power of nt. So the question is, use L'Hopital rules to show that the limiting formula as the number of compoundings per year becomes infinite, which is A equal to PE power of RT. For continuous compounding, n will become infinity. So the formula for continuous compounding is the limiting values of A when n approaches to infinity. So we can solve the problem. First, let's take the natural log of both sides. And then, since gx equal to ln x is continuous, we can interchange the functions and the limit on the right hand side. Because p is the constant, we can take it out of the limit. And then we can simplify the limit, which is t equal to ln bracket 1 plus r per n divided by 1 per n. Then the limit on the right hand side follows the intermediate form, which is 0 per 0. So we can use the L'Hopital rule, which is taking the derivative of both the numerator and denominator with respect to n. And then we simplify the limit, it will become rt divided by 1 plus r per n. After limiting the function, it will become rt divided by 1. And then we take ln p to left hand side, it will become ln a per p equal to rt. We change it to the exponential form, the answer will be a equal to p e power of rt. Therefore, we have shown that the limiting formula as the number of compoundings per year becomes infinite is a equal to p e power of rt. For example 2, suppose the formula for compound interest as the formula below, where p equals a principal, r is annual rate of interest, n is frequency of compounding, t is time in years, and a is total interest accrued over time. The question is, how if we compound £1 continuously at a rate of 100% for 1 year for greater and greater values of n, then we will get 1 plus 1 per n power of n, we will get Euler. Then, use this to derive the formula for continuously compounded interest, which is a equal to p Euler power of rt. We assume the limit does approach to Euler. Once we have that, we can look at the formula. And then we do some substitution. Let m equal to n per r, so n will become rn. Then we rewrite the equations with putting the m and n into the formula. F will become p bracket 1 plus 1 per n bracket power of n bracket power of rt. As n approach to infinity, the thing inside the large parentheses approach to Euler. So we can get the formula of continuously compounded interest. As for the main limit, the usual approach is to say we want to find L equal to limit bracket 1 plus 1 per n power of n. And then we take the natural log of both sides. Since gx equal to ln x continuous, we can interchange the function and the limit on the right hand side. And then we simplify it. Because the limit on the right hand side follows the intermediate form, which is 0 per 0, so we evaluate it with L'Hopital rule, which is taking the derivative of both the numerator and denominator with respect to n. Then, after we using the L'Hopital rule, we simplify the limit. The answer will become limit 1 divided by 1 plus 1 per n. When limiting the 1 per n, it will become 0. So the answer is ln y equal to 1. Then we transform it into the exponential form. Since the natural log of limit is 1, the limit itself must be Euler. So the final answer will become Euler. In conclusion, in calculus, the most important rule is L'Hopital rule. This rule uses the derivative to evaluate the limits which involve the intermediate forms. According to Menascero, L'Hopital rule is used to prove that the compound interest rate equation through continuous compounding equals p Euler power of rt. Compound interest rate encountered every day in investment, different types of bank accounts or paying credit card bills, mortgage, and so on. It helps people to manage their bank account easily like income and expenses. That's all for our presentation. Hope this video will bring some benefit to you. Thank you.